All right, boys and girls, one last problem. Problem number 6. The retina of the human eye can detect light when radiant energy incident or falling upon it is at least 3.9 times 10 to the minus 17 joules. Any less energy than that, and you just don't stimulate the nerve cells in your eyes to tell your brain you're seeing light. You need that minimum amount of energy. Right? For light of 590 nanometers, how many photons would you need to fall upon your retina to add up to that minimum amount of energy? Right? Now, the equation for energy that we're going to use, E is equal to hc over lambda. I'm going to use this because I'm given the wavelength. Right? If I was given the frequency, I would use E equals h nu, and I would plug in for nu, the frequency. Right? But I don't know the frequency. I know the wavelength, so I'm going to use this one. Right? Now, h is Planck's constant, 6.626 times 10 to the minus 34, and that's joules times seconds. The speed of light is 3.00 times 10 to the 8th meters per second. And that's all over the wavelength. Now, the wavelength was given to us in nanometers, but I need that in meters. So let's see, 590 nanometers is equal to 5.90 times 10 squared nanometers. All I did was take this and convert it to scientific notation. And then to get from nanometers to meters requires us to subtract 9 from the exponent, so I'll get 10 to the minus 7 meters. Right. How do you get from nanometers to meters? Well, again, you'd have to look at your metric prefix chart. From nanometers to meters means 9 jumps, and since we're going up the chart, we're going to subtract that from the exponent. So we're going to subtract 9 from 2 and get negative 7. Anyway, that's the number that goes in up here. It's 10 to the minus 7 meters. All right. Now, just a real quick look at our units. Joules times seconds and meters per second. The seconds will cancel. Now, up top I have a meter. Downstairs I now have meters, so they cancel. And I'm left only with joules, which is good since that's the unit for energy. So how much energy? Multiply and then divide. And let's see, looking this up, you get an answer of 3.4 times 10 to the minus 19 joules. And this is per every 1 particle of light, which we call a photon. Per every 1 photon of light. All right. Now, is this enough? Is the energy of a single photon enough to trigger the nerve cells in your eye to detect that light? Well, the minimum amount of energy is 3.9 times 10 to the minus 17. So this is not enough. All right. What we're asked to do is determine how many photons would we require to meet that energy threshold. All right. Let's see, I'll just put it right there. The number of photons we would need would be the total amount of energy required by your eyeball to actually stimulate your nerve cells. That total energy divided by the amount of energy per photon. All right. So the number of photons required to fall upon your eye to trigger something in your eyeball to say, hey, there's light there. I'm going to take the total energy, which is the energy given to me in the problem, 3.9 times 10 to the minus 17 joules. That's how much energy your eye requires to be able to actually sense that light. And the amount of energy per every photon, 3.4 times 10 to the minus 19 joules, which we got from up here. Just do this division, and you get 114.7 photons. Right? Now, you can't have 0.7 of a photon, so we'll just round up to the nearest whole number, which is 115 photons. And that's it for number 6.